We're now going to talk a little more about why LLMs are so important, doing so by highlighting their differences to previous traditional models the machine learning community has developed within the past. In terms of architecture, large language models and traditional machine learning models differ significantly in their architectures and capabilities. To reiterate, LLMs use transformer architectures, which are effective for handling sequential data like text. In contrast, traditional ML models vary greatly in their architectures. Depending on the specific task, the algorithms used could include linear regression, decision trees, or simple neural networks. These models are usually designed for specific applications and are not as adept as handling sequential data. Further, traditional ML models are inherently limited in their ability to process and interpret long sequences of input data, which can restrict their effectiveness in tasks requiring comprehensive contextual understanding. The training process for large language models involves using vast amounts of textual data from diverse sources, such as books, websites, and PDFs. The massive scale of the data helps these models understand and mimic human language patterns effectively, providing them with the ability to handle a wide range of natural language processing tasks. On the other hand, traditional ML models are usually trained on structured data sets that are well organized and often labeled for specific problems. The structured nature of these data sets means that traditional ML models are often tailored to solve particular tasks, lacking the versatility seen in LLMs. These datasets are also typically much smaller in size compared to those used for training LLMs. While this has benefits in terms of computational cost, it leads to less training data volume and diversity. Large language models are known for their incredible versatility, but they can also be fine-tuned for domain-specific knowledge, such as translation, summarization, and sentiment analysis. Fine-tuning refers to the process of adapting a pre-trained model for specific tasks or use cases. In the case for LLMs, it refers to the process of further training the model on a smaller specific dataset whose data is useful for a niche task. For instance, fine-tuning an LLM on a set of French literature will result in a model that is better suited to write dissertations and formulate arguments about French literary work. This adaptability is one of their most significant advantages, allowing them to handle diverse tasks with only minor adjustments. The ability to be tailored for specific needs makes LLMs highly valuable in different applications, from creating content to providing detailed analyses and answering complex queries. In contrast, traditional machine learning models are typically designed for niche tasks. For example, a model trained for image classification cannot be easily adapted to text analysis without significant changes. This lack of flexibility means that traditional ML models often require a complete redesign or retraining when applied to new tasks. The specialization of traditional models, while beneficial for specific applications, limits their versatility compared to the broad capabilities of LLMs. This fundamental difference highlights why LLMs are preferred for applications requiring a wide range of functionalities and quick adaptation to new tasks.